Good morning, students. Today we are going to start with a new topic, that is three-phase inverter. Now, three-phase inverter, this is the circuit of a three-phase inverter. Now, as you can see that this is an inverter circuit. And this is the VDC, and this is the three thyristors which are connected: T1, T3, T5, and T4, T6, and T2. And they are connected with a load that is star connected. You can choose that either it is star connected or delta connected. Now, three-phase inverter is mainly applicable for high power electronics like induction heating or welding, some heating generation, those kind of things. That means high power application when high DC to AC conversion is required, high voltage value, then we use three-phase inverter. Now, there are mainly two kind of conduction mode. One is 180 degree conduction mode, and another one is 120-degree conduction mode. So first we will let you understand what is 180-degree conduction mode. This is another one. Now as you can see that there are three figure. There are three thyristors, three connected in the upper layer and three connected in the lower layer. Now as you can see here, if I make a box to understand that when which thyristor is conducting. So as we tell that this is a 180-degree conduction mode. That means each thyristor will conduct for 180 degree. Next thyristor will conduct. Now if we see that T1 and T6, T1 and T4 are in the same in a series. So one will be connected in a forward bias, one will be connected in a reverse bias. This is same with the T3 and T6, and this is for T5 and T2. Now, suppose T1 is switched at 0 degree. So T1 will conduct up to 180 degree. After that, T4 will start to conduct because it is just the reverse bias of the T1. Now, after T1, the next phase thyristor is T3. Now we know that phase voltage is 120 degree shifted. So it will be started with a 120 degree shift, that is it will start from 120 degree. So it will conduct up to 300 degree because it will conduct 180 degree. So after 300, T6 will start to conduct, and T6 will conduct up to 180 degree. So where it is conduct from 300 to 360, that is 60 degree, and here it is conduct from 0 to 120 degree, that is total conduction period of T6 is 180 degree. Now after T3, T5 will start to conduct. So T5 will start to conduct from 240 degree. So it will be conducting from 240 degree to 360 degree, and then from 0 to 60 degree. Okay, so this will be the conduction period for each of the thyristor. Now if we try to draw the figure of the conduction angle of the different thyristors, so we will see that at each time three thyristors will be simultaneously connected. For first 0 to 60 degree, T1, T6 and T5 is conducting. So if we draw the equivalent circuit diagram considering T1 and T6 and T5. So T1 and T5 is connected in the upper side, T6 is connected in the lower side. Okay, so if we draw the equivalent circuit, this is our VDC. So VDC current will come from T1. T1 and T5 are connected in a same node. So T1 is connected with A terminal and T5 is connected with C terminal. Now C terminal is having a Z impedance, this one. Same, A also has a Z impedance. So they are now connected with the neutral terminal. The neutral terminal, there is a Z impedance, and that is connected to B terminal, that is T6. So that means the current will flow from this part. After coming to this point, current will flow in this portion and this portion. Then this current will flow and then it will come like this here, and this current will flow come like this here. So both of these two current now goes to this path, and then it will follow here and going back to VDC. So this is will be the path. So we can find out that VAN and VCN, both of them are in parallel connected. So if we apply the voltage divider rule, so we can find out VAN, which will be equals to VDC into Z by 2, and the total impedance is Z by 2 by Z. So VDC will be VAN will be VDC by 3. So your VNB will be VDC total voltage minus VAN. So that will be 2 VDC by 3, and as it is NB, so BN will be minus 2 VDC by 3. So if we draw for 0 to 60 degree, your VAN is VDC by 3, whereas VBN is minus 2 VDC by 3 and VCN is VDC by 3. Now if we draw for 60 degree to 120 degree conduction mode, so we will see that we will draw this circuit where uh, it is T1, T6 and T2 is conducting. So T1 current will coming to A, then goes back, it will come like here, current will follow this path and it will goes to N, and then this will goes to C and this will goes to B. So B will be flowing to this and C will be flowing, sorry, C is flowing like this. So after that C is coming here and B is coming here, then it will be coming to VDC. So here we can see that if we find out VAN, that is equals to 2 VDC by 3, and VNC and VNB, both of them are same. So VCN and VBN will be minus VDC by 3. So that will be minus VDC by 3 VCN. Here also minus VDC by 3, and it will be 2 VDC by 3. So in this same way, if we try to draw the each circuit, if we try to draw our each circuit, this is our 120 degree to 180 degree conduction mode. Your VAN and VBN will be equals to VDC by 3, whereas VCN will be equals to minus 2 VDC by 3. So we will go on to draw this circuit up to 2 pi. So your pulses will be look like this, where you can see that VBN is shifted from VAN with 120 degree and VCN is shifted from a VBN is 120 degree. So this will be your phase voltage. Now we know that our line voltage, we can draw VAB, VBC and VCA. Now VAB equals to VAN minus VBN. So if we minus this to VAN minus VBN, so VDC by 3 plus 2 VDC by 3, that will be VDC. So in this way, if we go for 120 degree, 60 degree to 120 degree, it is 2 VDC by 3, it is VDC by 3. So that is again VDC. So like this way we will get our phase voltage. So this is our, sorry, like this way we will get our line voltage. So this is our line voltage, this is our phase voltage. Now if we find out the RMS value of the phase voltage and line voltage, our phase voltage RMS value, it is conducting from 0 to pi. So 0 to pi V phase square, this will be the function, and your V phase voltage will be look like this, root 2 by 3 VDC, and your V line voltage will be VDC into root 2 by 3. Okay. So this is your 180 degree conduction mode. So we know that this is mainly applied to the high voltage application where high DC voltage have to be converted to AC voltage. That's where it is being applied. Now, if we going to analyze the Fourier series expression for this 180-degree conduction mode, we see that this is our V phase voltage. So as we can see that for find out the Fourier series, why we are trying to find out, because this is in shape in the square wave, so we want to make it as close as possible to the sinusoidal wave. Okay, so for Fourier series expression, we already know that for Fourier series there are three things. One is A0, one is AN, one is BN. Now for the odd function, A0 and AN is 0 and we have to find out BN. So first check it is a odd function or not. Yes, it is odd function because f of omega t is equals to minus of is minus of f of minus omega t. This is the odd function. Now let's check it is a half wave symmetry or not. Half wave symmetry means f of theta, that means if we choose this point, sorry, minute. If we take f of theta, this point is equals to f of pi is equals to minus of f of pi plus theta. So this is a half wave symmetry. Now let's check it is a quarter wave symmetry or not. For quarter wave symmetry, we already know that f of pi plus theta equals to f of pi minus theta. So f of pi plus theta is this portion. F of pi plus theta this portion and f of pi minus theta this portion, whereas f of 270 plus theta this portion and f of 270 plus theta this portion, so they are similar, so we can say that is the odd function and quarter wave symmetry. So we know that for the quarter wave symmetry we just have to find out the wavefrom up to pi by 2, that means up to this position. So if we find out the Bn, its value will be look like this. So now if we try to find out B3, we see that it is 0. So B6, B9, all the values are 0. So we can comment that the phase voltage waveform doesn't have any triplen harmonics. So third order harmonic, triplen harmonic is eliminated. So 3, 6, 9, 12, its order harmonics will be equals to 0. So you only have 1, 5, 7, 13, 17, this harmonic. So we can write n equals to 6k plus minus 1, where k equals to 0, 1, 2. So we can write our VAN, which will be equals to n 6k plus minus 1 2 VDC by n pi of sine n omega t. Why? Because B1 is equals to this value. So we can write this. So from here we can find out our V01 RMS, that is root 2 VDC by pi. We have already find out it in the single phase half bridge inverter. So go to that lecture and you can find out how this is can be find out. So then we can find out the THD, that will be equals to 31%. Now this is we have find out for 3-phase full bridge inverter for phase voltage. Now we will see what will be the Fourier series for line voltage. Now this is the Fourier series. Now this function, if you see that there is a trick, this is the voltage waveform, line voltage waveform. Now from this waveform we can say that this is neither an odd function, neither an even function. So that means its an bn is not equals to 0. So now let's make this function as an odd function. Now how we can make this function as an odd function? Now let's shift it by minus 30 degrees. So that means it will start from here and it will go up to 150 degree and it will be going from why this is not a odd function, because f of theta is not equals to minus of f of minus theta, because here f of theta has some value, but f of minus theta, that means this part, is equals to 0. So that means this is not our function. But if we shift it by 30 degree, say, then it's f of theta, and if minus of f of minus theta is same. So that means this is odd function. So odd function means we have to find out the bn value. So we can write this expression. Now how we can write this expression? If we see this waveform is look like as a single PWM technique. So we have already find out for a single PWM technique, this is the value. So we have just put that value from here. You can go there and the single PWM technique and find out how to find out this value. This will be the value. So no worry, this is already has been reduced in your class. So this will be your value. So here d equals to 60 degree, because if we choose this as a 2D, so this is 120 degrees, so d equals to 60 degrees. So this will be your value. Now if we find out the Fourier analysis of this waveform, this is the shifted waveform. So this means that has to be shifted. It is shifted by minus 30 degrees. So to go back to this position, it has to be shifted by plus 30 degrees. So that will be added by n pi by 6. So your line voltage Fourier series waveform will be look like this. Now I have shown it for 180-degree conduction mode. You will have to do it by yourself. The 120-degree conduction mode, it will be same. Just you have to keep in remember one thing, that for 120-degree conduction mode, each switch will conduct for 120 degree. So if we go to our first figure, let's go back there. If we go to our first figure, if we go to our first figure, so here we can see that it is conducting up to 180 degree. For 120-degree conduction mode, you will be doing by this by yourself. For 120-degree conduction mode, what happened? It will conduct up to 120 degree. So from 120 degree to 180 degree, there will be no conduction. So one place will be left blank. Okay, that means it will conduct from 0 to 120 degree. So from 120 degree to 180 degree, it will be left blank. Same for the T3, it will starts to conduct from 120 degree and it will goes up to 120, it will goes up to 240 degrees. So 240 to 300, again it will be no conduction. So if we find out the figure in the similar way, then you can see that only two thyristor will be simultaneously working. So by that the process will be same. You will find out the waveform for the phase voltage and line voltage, and from there you can also find out the Fourier analysis for the three-phase inverter for 120-degree conduction. So as I have told you already, so this kind of inverter is not applicable in our home appliances, because in our home appliances it is single phase inverter. But three-phase inverter is mainly applicable where the high amount of voltage has to be converted from DC to AC. So this is up to today's class. Next class we will start and that with the current source inverter. This is the last topic of your inverter chapter. So thank you students.